pretty sure EHS is going to come after me now.
No problem.
But while doing the experiments, you do have some time to just dance. All right. Okay, so as Hikshan initially mentioned, that I will be presenting upon the topic, which is detection of COVID-19 and flu virus simultaneously using antibody functionalized graphene field effect transistors. So why are we coming up, or why do we want to do that? I mean, since 2019 or the end of 2019, COVID-19 has been a part of our life. Like, it is just there all the time. And we have seen in the beginning, especially, that there are multiple layers to the problem of COVID-19, especially when you look at the way it has played out on a large scale. Or on the large human scale. Had it been contained initially, we probably wouldn't have gotten to the point where point of care devices, which basically mean that you can have very quick and fast testing electronically, and then have it uploaded to the cloud so that you can have remote testing anywhere and anytime without the necessary intervention of a skilled personnel. So COVID-19 definitely opened an opportunity for this, but with a very heavy cost. And we have seen that playing out at a very large scale in, very high density areas like New York, or the rest of the world. We can say in high density areas like cities in China or India or Seoul. So the amount of people over there is very high. And when you have a very virulent virus like COVID-19, SARS-CoV-2 over here, we want to contain it as much as possible. Now that is, that did not happen. So the next step of mitigation over there would be early testing, quick testing, and so that the treatment can be, or the further protocol that the person would have to undergo, that would be decided accordingly. So right here on the left side, we can see that we have a huge problem. Like whenever we have been living with COVID-19 for the past 2 years, but even now, whenever there's a slight surge due to a new variant, we see that there's we start having bottlenecks in the testing facilities, and you see people in high density areas again lining up for so long, and that's not a very safe situation to be in, because that's what we want to avoid in the first place. We don't want aggregation of people, but these kind of situations force the people to come together. Then, coupled with that, we also have the guidelines from CDC, which says that earlier, especially if the person had not been vaccinated, the recommendation was that you have to quarantine for 5 days before actually going for the test. And the reason for that, again, was number one, the shortage of testing kits. And the second thing was also that whatever test options that we have available with us right now, they do not give you any accurate information until 5 days later, or estimated 5 days later, because we need the viral load to build up in the body so that it can be detected by the available testing methods. So this also highlights that whatever testing methods we have available commercially right now, their limit of detection, or their limit of detection is not low enough to pick on the initial buildup of viral load in the human body. And what are the test options available to us? We have the antibody testing. We have the most popular one is our RT-PCR, and then antigen testing. Now, with the antibody testing, the problem is that it is only applicable if you have had COVID in the past. It's not a diagnostic tool to tell you whether you have COVID right now. It's just going to detect the antibodies that have been developed due to the introduction of virus or replication of virus into the human body. RT-PCR and antigen test, between them, antigen test is the faster one, but it is also something which has a lower accuracy. It takes 15 to 20 minutes to get you to get the result, but it is not always. It's like a screening tool, but we would not call it a diagnostic tool because it cannot. It sometimes has false negatives and false positives as well sometimes. And RT-PCR, which is the most popular and most preferred, is high accuracy. But the problem with it is that the turnout time is low. You go for the testing and you will need at least 1 day before you get the results. And that's fair because when we look at the testing procedure that the sample swab, the nasal swab sample that we take from the nose and use it for the RT-PCR testing, the steps over here are highly intricate and they require skilled personnel. And they also, in the process, the processing of the solution and sample takes a lot of time. So there is at least 5 to 6 hours that is required before from the collection of the swab and then getting the result. Now, if you are going to have this problem with 1 million people, especially in high density areas like New York or again cities in India or China, this is not the most ideal case to deal with. And unfortunately or fortunately, I would call that this is the best option available to us. So now the question is, what if you can reduce the testing and the detection time drastically? When I say the testing time, it basically means that what if instead of the 5 days prescribed by the CDC, you can get tested 1 or 2 days, and after 1 or 2 days of exposure? And also, what if instead of taking 5 to 6 hours of accurate detection through tests like RT-PCR, we can get the result in 12 seconds? So, as Marine Lebois put it in one of her LinkedIn posts, she basically was highlighting another sensor. But to put it in perspective, what if we have a sensor which is sensitive enough to have femtomolar detection limit? So if we have very low limit of detection, that means that we will be able to test people earlier. That means, and if we have a faster detection mechanism, that means we can get the result on time. And that means that we can also ask the patient to get treated earlier. The patient will have the option of getting treated earlier or faster. One more thing that is a problem with flu strains like COVID-19 especially is that they all belong to the coronavirus family and they have very similar symptoms. So one more problem that we would often face, especially in the fall months, is that the flu season is high. And then on top of that, you have the problem with COVID-19. Both of them have very similar physiological responses. So how do you detect whether the person is having COVID-19 or flu? And since the treatment is different for both of them, then treatment and containment protocol is different for both of them. You would want to know what the person is suffering from so that you can tailor make the protocol for the person, whether the person needs to be quarantined or that person needs to be put on antibiotics immediately. So what we did at Akinwande Lab is try to shoot all these problems by making a field effect transistor using a 2D material called graphene. And in this field effect transistor, basically we are able to detect COVID-19 and flu separately at the same time. So if let's say if we put the sample of a person who is suffering from COVID-19 or let's say we don't know whether the person is suffering from COVID-19 or flu. And if we put in that sample of the nasal swab of the person into our device, we will be able to identify whether the person is suffering from COVID-19 or flu, depending on how the device gives out the reaction. So this is just the basic schematic of the device. That on the left side that you're seeing, we have graphene laid out in a field effect transistor between the source and drain. And we have 4 chambers over here. One chamber is modified with the antibodies of COVID-19. The second chamber is modified with the antibodies of flu. And the third and the fourth chamber are the control chambers, which will be able to identify whether the results that we are getting are true positive or not. On the right side of the slide, we can see this is an optical image of the device that we have. If you look at it a bit more closely, we'll see that there are 4 quarters over here. Each quarter is basically one FET or field effect transistor, which has been modified with COVID or flu and the respective chemical functionalization. Before I go into greater detail of the device, I would like to just make a brief introduction about graphene. What is graphene and why are we using graphene? So graphene was discovered in 2006 or 2000. It was discovered in 2004 by Nozolov and James, and in the University of Manchester. And basically, graphene is just a single layer of carbon atoms arranged in a hexagonal structure. So we may have studied in our elementary schools that graphite is basically single layers of carbon held together using the van der Waals forces. And when you are able to isolate one of these layers, you get graphene. Now, why is graphene so suitable for bioelectronics? Before getting into that, I would say that when graphene was discovered, it was touted as a wonder material that could do pretty much anything. And it was also thought that at one point it may be able to replace silicon in our electronics. While a lot of research has been done into that, graphene was also being used a lot of research was also being done in a very unlikely field of graphene being used for biosensing. And turns out that it is an excellent material for biosensing for a lot of reasons. Number one being that it's a carbon structure, that it is biocompatible with the humans, and that also means that if you're putting in any biological matter over here, that matter is going to survive because it is non-toxic. The second thing is that its electronic properties are really good, so it makes it an excellent transducer. Whatever reaction that you're seeing on the surface of graphene, that is going to be reflected into the device make that it is. For example, in our case, we are using it as a field effect transistor. So we technically can modify the layer of graphene with any antibody, enzyme, or DNA that we want to detect for. So graphene basically comes with a very high versatility with it. You can use it you can repurpose graphene to decorate or modify it with the antibody or enzyme or any biological matter of interest to detect whatever we want to. In our case, we have decorated or modified the layer of graphene with antibodies. We have, since our interest is COVID and flu, so we have decorated the surface of graphene, the FET with flu antibodies and the COVID antibodies, and then we detect whether depending on the response of the device, we can tell whether the person is suffering from COVID or flu. So just a brief methodology on how this device is being constructed and functionalized. So we're using P-base. It's one of the organic linker reagents. So we are using to attach the antibodies to the surface of graphene. So graphene, the kind of graphene that we're using on this FET or the field effector transistor over here is a CVD grown chemical vapor deposited graphene that usually does not have any dangling bonds on top of it. So we need to modify it in such a way so that since we don't have any dangling bonds on it, it will be hard to functionalize or attach any antibody or any biological matter on top of it. So in order to introduce antibody functionalizing space over there, we first modify the surface of graphene using P-base, which is a pyrene-based molecule. Then after that, we have the antibodies, which basically get stuck to the surface of P-base over here. And then we follow it up with blocking using reagents like PEG, polyethylene glycol, or ETA, which is ethanol amine. We do the blocking so that we make sure that the rest of graphene, which may not have been functionalized with P-base, that is, or some of the P-base which has not been occupied by the antibodies, they get blocked so that we won't have any misresponse on the surface of the chip. So once we have the antibodies fixed, when we do the when we introduce the protein or this sample, if it is a COVID sample, then it will go and bind with the COVID antibodies, and if it's a flu sample, then it will go and bind with the flu antibodies. So if in this device, as I had mentioned earlier, each chamber or each quarter has been functionalized with the antibodies of interest, COVID and flu. Yeah, so coming more into the detailed and science stuff over here is that we just saw that to prepare graphene for detection of COVID and flu, we made it undergo several steps of functionalization, and we used electrical. There are two ways we have been able to identify that the whether the functionalization that we were doing is successful or not. So one of the ways is through electrical characterization, in which we do a very normal IV curve on the FET by sweeping the gate voltage around in a certain range, and then see how the graph changes. So if we look at the pointer over here, as we keep introducing different functionalizing agents on top of the graphene, we see that the graph shifts to the right in different directions. So what happens with our particular functionalization step is that we have bare graphene, which is in black, and then when we introduce P-base to it, it shifts to the graph shifts to the right, and then when we add antibodies to it, it remains almost there, and then we add the different blocking agents like PEG and ETA, and then we see the shift of the graph going back. So it just indicates that how you keep adding different functionalizing agents, how the layer of graphene is getting doped in different how it is getting doped, whether it is getting N-doped or P-doped. And this has been also shown in a lot of papers earlier. In the literature, this is a very standard way of identifying whether the functionalization that the device or graphene especially is going is all right or not. Also, other ways of optical of characterization is optical characterization. Here we have used Raman spectroscopy to identify whether we had the attachment of the second reagent that we were using here, that's p-base. So we can see very clearly that upon addition of p-base on the surface of graphene, there's an extra peak at 1623, which basically through literature again identifies that, yeah, we have a layer of functionalization that we are looking for. So after successful device characterization, we come to the main part, which is the testing. So the testing setup, what we have in our device right now is that we fill the chip uh, with, we introduce the sample, basically the protein samples of the virus particles that we are interested in. So just to identify whether the device is working properly or not, um, what we do is first we introduce the SARS-CoV-2 protein viral particles in the solution. And since we have four different FETs on the device, we have four curves going. We basically have four current data that is being recorded from the device. And over here, if we focus our attention to the graph, we can see that one trace over here is with respect to the SARS-CoV-2, which basically means that the current reading that we are seeing over here is coming from the FET, which has been modified with COVID antibodies. Then the second curve that we are looking at is the flu curve, which means that the current over here is coming from the FET, which has been modified with the flu antibodies. And the third one, which is tween 20, that is coming from one of the controls. So what we did over here, we added different concentrations, starting from very low concentrations of SARS-CoV-2 protein viral particles. And when we introduced it into the common device, the only area or the only FET where we saw the reaction was in the channel which had SARS-CoV-2 antibodies in it. So, and we did not see any reaction in the FET, which had the flu antibodies on it. So this is very significant in identifying that, yes, the device is very specific. When we introduce the SARS-CoV-2 antibodies, it is SARS-CoV-2 proteins. It is only seeing reaction, or it is only interacting with the antibodies of SARS-CoV-2, and we are seeing a very sudden drop in current over there. And we do not see that reaction in flu. So this means that the device is specific. Now, again, in the next iteration, when I introduce the flu protein in the solution, I see that there is a sudden change in current only in the trace that is corresponding to the FET, which has been modified with flu. And we do not see any change in the trace, which is coming from SARS-CoV-2. SARS-CoV-2 modified FET. So again, this just highlights the fact that the device is extremely specific, and depending on the sample that you will be putting into the device, we will be seeing the reaction in the corresponding pocket or quarter accordingly. Why we were using a third control, a control over here, tween 20 here, was just to make sure that we are not receiving or reading any false positives over here. The expectations with this kind of chemical passivation is that nothing should be interacting with the surface of graphene. We basically chemically pacify the surface of graphene with everything. And so whatever we are putting in over there, it should not be influencing any change on the surface over there. Yeah, just one more result, again, just highlighting the sensitivity and the selectivity of the device, is that we can see that whenever we are introducing the COVID-19 protein, the COVID-19 protein is, we are seeing a high reaction or a signal response over here, which is 4.5%, as opposed to the same flu protein interacting with the COVID-19 antibodies, and we are not seeing, we're barely seeing any reaction over there. So we can, and the same goes for the flu antibodies. So it just says that it is a highly selective and selective device. One more thing to identify or see over here is also the time response. We are seeing the results within 12 seconds. So this is a very good thing, because as opposed to the commercially available tests that we have right now, we are able to detect things faster. It's a very short turnaround time, which is definitely going to help and mitigate the possible problems that we would have from low response from long response times. Yeah. So just in conclusion, also one more thing I think that I forgot to highlight over here is that we have been able to see very low limit of detection over here. We've been able to record proteins at the concentration of attogram at sub-attogram level, which is extremely low. And that also means that the testing time that you would be going for, instead of 5 days, instead of waiting for 5 days before the testing, you can go for testing probably in 1 or 2 days and still have a true result at your hands. In future, this kind of device is right now, it's very versatile, and it can be multi-purpose. It can be repurposed with any antibodies that we want to work with. Right now, since COVID is at the top of the problem, is the top problem right now, so we are using it for COVID, but basically you could use it for any other detection like ferritin detection, or any other, if touch wood, if we have any other possible pandemic in the future, this is one of the devices that can be used to mitigate the things faster. Yeah, that's about it. If you have any questions, ready.
All right, thank you, Neelotpala, for your excellent presentations. So since we are almost running out of time, probably we can only accommodate 1 or 2 questions before we come to the final remarks. So does anyone have any questions? All right, I have a quick question. So basically you're developing a like graphene or functionalized graphene to replace the normal like test for or detection for the virus, right? Or you can just doing multiple detection for the virus. I just kind of wondering, what kind of the device are you going to make? Is it something that like replaces cotton swab that you can directly get the data from the test, or you just like, you know, I was just wondering what kind of the final device are you going to make?
So the final device, what we are thinking is that we can have a plug and play device. You know, we have this device and we'll have a reader. You could probably even, if we are able to get a good Bluetooth capability, we can even read, just attach it, or if we have an extension to the mobile phone, we can just attach it to the phone, and then whatever reading that you're getting, I mean, you can get the data analysis in real time and then just see it immediately whether the person is having COVID or flu right now. So that is, we are basically looking for a plug and play kind of device, because we have very quick electrical readouts over here.
Okay, thank you. We seems got a question from the chat. So can you just answer that questions? Or I can repeat questions. So Amnor is asking, is there any chance of having false negative results due to the presence of any other viruses?
So that is a possibility, and that's why we we have 4 chambers on top of it. One sec. So if I just go back to the schematic, we have 4 chambers over here. One is chemically pacivated and one is bare. They're basically serving as our control FETs over here. So if you're seeing any other virus, most probably we're not going to see any reaction in COVID-19 or flu. And then if with the chemically passivated, we are expecting that there should not be any reaction over there, and with the bare, we are expecting that whatever you're putting, you should be seeing a reaction. So basically you can make a truth table out of it, and if there, I think the device is should not be able to detect any other viral particles. And in our test, we have also tested it with a third biological agent like BSA to see whether we are seeing any reaction or not, and we haven't seen that till now. So I right now we haven't seen any false negative, so I think we should be okay. But we have to test with more viral particles. Still, we have just tested it with just one right now.
Thank you.
Yeah.
All right. Neelotpala, could you close your slides so that I can bring my slides?
Yes.
All right. So thank you, Neelotpala, and our audience again for joining us. Now I would like to invite you for our next talk, which is entitled is Quantitative Characterization of a Microdialysis Probe using ethanol as test analyte. And our next speaker is Xiang Li. The time is exactly next week, same time. So with that, I would thank you again for your attendance and wish you have a good weekend. See you next week, everyone.
Thank you.